My name is Zhou. Good afternoon. I'm giving a talk titled as Prediction of Short-Term Driving Intentions using recurrent neural network, using sequential data. This is the work that I initiated at this company called Athena Robotics, which is my own startup previously, and this is the initial team here. And then right now I'm working with my current team, Borgat, with my team member Andres, Zhou, Chang, of course, alphabetical order. All right, let's get to the detail of the talk. So there's 5 parts of the talk: motivation, and then I talk about intentions part, and then I talk about behavior part, and then put all this together. We can build something we call safety and reliability platform, and then of course finally the summary part, the conclusion part. All right, so we go motivation first, right? So why are we all sitting here, late Friday afternoon, talking about this? So there's a motivation, a reason for that. I don't know how much of you know the self-driving cars, right? In the Bay Area, in Silicon Valley, it's probably very popular, to talk about self-driving cars. And this work here, focusing on the prediction part of the intention, humans' intention, and behaviors, and of how they use the road, right? And because it's of great importance for planning, especially the decision making in a self-driving car. So it's a very critical component there. And even few seconds, right? When I say few, it's actually 1 to 2 seconds predictive power. Of course, in a highway, right? Sorry about this. That predictive power is very important, right, to ensure the safety of self-driving cars, which is why I call it the most valuable 1 to 2 seconds, right? Well, it is not uncommon that most of our human beings, right, like humans, like us, right, we can rationalize in advance various on-road behaviors, intentions, as well as their, risk associated with them. This reasoning skills is very difficult and challenging for computers to learn, right? So here's one, you might ask, like, what do I mean exactly by behavior? So I'm gonna play a little demo here. So you can see like people crossing street like this, right? And they're crossing, and then all of a sudden everybody starts running. And this is actually a group behavior. If you see like 2 or 3 people start running, you will follow them. This is what I mean by a behavior, right? So this is like a natural human behavior, and our brain can rationalize it, why people are behaving like this. Because it's easy, right? Green lights switching to yellow. So people tend to run at the end of this goal across the street, right? That's what we call reasoning here, rationalize everything, right? So that's what I mean by behavior, and this is the focus of this talk. A little bit about the background of self-driving cars, in case you don't familiar with the concept here. It's car will drive itself, right, with sensors, software, everything together. And this is just my opinion for the current status of the self-driving cars, which I use this metaphor I call 5 sense versus 1 brain metaphor. Everybody knows safety is a problem right now, or showstopper for commercializing a self-driving car. And since we're dealing with humans, right, human uncertainty is the thing that makes everything difficult here. So in the past few years, in my opinion, everybody's focusing on the 5 sense, right? Where am I? The location, HD map, what is around me, the perception system using sensors, right? These are building the 5 sense, which is very important, of course. And then now we start to think about, what's next, right, for self-driving cars. So now what? Now we're focusing on this 1 brain, and we're talking about things like why people are behaving like that, right, the behavior part. What are they going to do next, which is the prediction part. And finally, what should I do, right? How do I drive my car? That's what we call decision-making, the planning part. So, that's just my take, of course, of the current status of self-driving cars. Then, the thing we're building here in our team, with my team, is because we want to build a AI system, right? For example, to train and test the AI for the autonomous drivings, right? I give a very concrete example here. For example, anyone wants to build an AI system, I give you an example, collision forecasting system. How do we build it, right? Well, I guess how do we build it, that's your job, right? But the second job is what I'm trying to, basically convince everybody here that we need this platform is how do I make sure it actually works, right? So if you look at the center one, right, that's our platform, for example. It consists of a few components, very important components. The first one is traffic scenes, right? We provide all these scenes, and our focus is on the collision scenes. You might hear this a lot, so-called unprotected left turn, right? I read that in news, right? Everybody read that in news publicly. The Waymo car has problems with unprotected left turns. On runway drivers, it's an extreme case, right? You have runway driver comes in and you want to avoid that. So these are all the challenging scenes. What we call in AI world is called long tail events, right? We're providing those long tail event scenes in this platform for people to test. And then the second component is the behavior part, right? So everybody is behaving, like I said. They have a different behavior manners, San Francisco, New York, all kinds of behavior, drunk drivers, right? We need to provide that for people to make meaningful tests. If everybody is behaving like dummy, a robot, right? Just go straight, then there's no point to test everything. And of course, once you have behavior, you execute your goals using this, what I call intention. So you have intention like, short-term intention, like make a left turn, make a right turn. You have your long-term intention, which is more like a goal. I want to pick up my daughter from school, right? That's my intention. So all these components, we build up all these components in our platform, right? And then we provide that, for testing any component in the AD stack, like perception, SLAM, path planning, vehicle controls. And this is very important for us, right? For the AI guys, right? We are doing, of course, training and testing, right? We have data come out of the platform. We have ground truth. We call it ground truth, which is basically what this guy want to do, right? And then we want to provide metrics experiment. We can measure your system, how good your collision forecasting, your collision avoidance system is, right? So that's a training and testing process out of our platform. I actually built this myself. The initial version is open source. I put it in the Docker. You have a different version of the Docker. You have the code. And you have it in the AWS. Wherever you can find them. All right. So let's talk more about the algorithm side, the science part, right? So I'm using here a thing called recurrent neural network, which is just an architecture of neural network, right, to predict human intentions. And here I'm focusing on the key word is short term. So I'm not dealing with long-term stuff that you want to go home, you want to go grocery shop. I'm not doing that. That's not the thing we're talking about here. We're talking about the short term, relatively short term, and those are the fundamental units that constitute the more sophisticated driving goals. I'll give you a concrete example here. So if you want to do a overtake. You're driving. There's a slow car in front of you. You're getting very, annoyed, right, or impatient about the car in front of you. So you're going to decide overtake. And this is a complicated, a goal, a task to achieve, right? Relatively complicated, right? So you're going to lane change first, right? And then you're going to find a spot, and then you go accelerate, and then you lane change back to wherever your comfortable zone is. So that's just a concrete example. Now, if you break this goal into the small pieces, it just looks like this, right? You have, straight, which is lane keeping, and you want to change to the right lane, right? You want to change to the left lane, and then you want to make a left turn, U-turn, overtake, right? All these are, short, relatively, the previous ones are more like relatively short-term things. These are the things, like the fundamental things that we can actually use. I'm not saying our recurrent neural network is the only tool, but it's just one of the tools you can use to do these experiments, to make sure everything works. So if you want to know more details, my paper is in the archive right now. You can look at it about more details. All right, so the first thing we talk about how to do this experiment, of course, data, right? We are data science, so data comes first. If you don't have data, you don't have any things to build out on top of that, right? So we talk about data first. Now, in this platform, everything, when I say platform, it's the previous version, the initial version, of course. Everything like training, inference, right? Every data is recorded at 5 Hertz, right? Each timestamp, you have all the raw sensor data, like images, LiDAR, point clouds, everything, GPS traces, an object list, right? And then we call a sequence out of this time series data. So we take 6 frames, for example. I call it a sequence. I have 2 versions of sequence. One is a short one, which is only 6 frames, right? So 200 milliseconds times 6, you have 1.2 seconds. That's that 1 second I'm talking about. The other one is a relatively long sequence, which contains 12 frames, right? That's 2.4 seconds. This is like a relatively long sequence here. Now, this data, I think is all open source, but right here, so we have like ABCD 4 different data sets, right? 2 are for highway driving, where every car is going faster, of course. C and D are for urban driving, it's slower, And then you have traffic light, you got to stop. So it's relatively more complicated. And 12 frames, 6 frames, already talked about that. So long sequence, short sequence. I have this many, a few 100,000 sequences collected out of this platform. They're used for training your neural network, and some of them are training for testing or cross-validation. So, and here, when I say intentions, I build a common set of intentions, of course. Like I just said, when you're driving, it's not very complicated in terms of like short-term stuff, right? It's only go straight, lane keeping, or you want to change lane to right, change lane to right, to left, to right, and you want to decelerate, accelerate, right? These are very fundamental units, that you're using when you're driving for human drivers, right? So I'm gonna play another demo, show you like what I mean. So lane keeping, right? Lane changing. Sometimes accelerating, sometimes decelerating, right? And this is what I call skeleton mode, where you just rip off all the rendering graphic stuff. You see everything clearly. For urban driving, it's a little bit more complicated because you have a traffic light in the way, right? And then you're gonna full stop or in front of a traffic light. So it's a bit more complicated for urban driving. All right, so this just to give you a little sense of what data comes out of the platform. Now, we have the behavior intention kind of thing, more like software thing, algorithm thing. Now, how do we get into the details? Now, how do we implement our goals? I call it execution of our intentions. Now, this gets into the car business, right? Because we're car guys, right? Quote unquote car guys. So we have our own cars, right? In our platform, all vehicle dynamics are parameterizable, right? You have engine torque, brake torque.
Sorry.
Yes.
We should not have two meetings in one room. So please focus. I would like to focus your speech. And if you translate, maybe.
Oh, you're talking about trans. Oh, I don't know.
It's very noisy.
That's actually not my.
Yeah, you create.
The problem is that if I stand there, I cannot hear. And actually, when I stand this far, it's already a little unclear to me. I cannot hear very well. I think if the mic is not performing well.
I don't know. This is the first time I'm having a conference without any moderator.
You can actually move yourself that way, so this can be clear, so that I can at least hear well. Because we have media guests here, and they definitely might help me understand what he's talking about. And this is the whole goal of him presenting. Right?
You want to come closer to me, maybe?
I was standing in front of them. If that's
There's a
better.
projector here, so she has to be there.
Oh,
The point here is that while you're paying attention to the presentation,
I know. I'm distracted myself a little bit as well.
you should just move over there. We'll take about 20 seconds.
Can we, accommodate for some, You mind?
他们也说，他们刚刚也是说挡着他们了。I can stay here, but if you don't think you will be bothered by it.
Okay. Sorry about that, guys. Sorry about that. All right, shall we continue? Okay. Alrighty. Cars, yes, we're talking about cars. So every car dynamics is parameterizable, right? Suspension, wheels. These are our car details, right? If you don't care, fine. But I'm just telling you that car needs to be parameterized. Like if it is SUV or truck, it's different, right? Car dynamics are vastly different between different cars. And then each intention basically is fulfilled by generating a path, right? We call it path planning, right? You plan a path and then you follow that path. In terms of algorithm, the control algorithm is kind of very straightforward right now. It's just a simple PID controller. So you have a proportional differentiation and the integral, right? For the three parts. And that's how I'm just describing how I generate those data, right? And then for this particular experiment, a rule-based planner, it's similar to like IDM, intelligent driving model, to generate whether I should lane keeping or lane changing or left turn or go to some collision scenes, whatever. So this is how I generate different execute different intentions. Okie dokie. Now let's talk about training and testing, right? Don't be scared by this large table here. I'm gonna walk you through about the numbers. Since we're doing like sort of like experimental science, right? We want to do measurements. So the modeling side is kind of straightforward. It's if you look here, it's basically a 12 frames sequence, right, of a recurrent neural network. It takes input from the bottom layer X. It goes to some cell, either LSTM or GRU cell, and then it goes to the output layer, where the output layer generates different intention classes right now it's using softmax, right, with cross entropy. And then you train everything, because you know the ground truths, you have the data, you train everything, and then you do your cross validation, which is this number's meaning here. So I'm gonna walk you through here. Right now I'm only showing 3 different intentions, 0, 1, 2. 0 is lane keeping, I go straight. 1 is I go right. 2 is I go left. I wanna see how good a recurrent neural network can detect or predict these intentions. And these are using only very minimum data set, like just the lat and long, right? Longitude, lateral and longitude coordinates. And this I'm using a bit more, using the head angle, right? You can add more stuff. You can use the signal lights, traffic lights, everything, of the car. But I'm just giving you a very basic example here. And then you're using different cells, LSTM cell or GRU cell. If you're not familiar, I'm not sure what my audience background is about LSTM, GRU, but if you're not sure, definitely you can find somewhere else to check the details of the model. So these numbers here, on the left, we call it precision. On the right, we call it recall. And what is precision? What is recall? Precision is basically how many selected are relevant, right? You select how many intentions. You want to know how many of those are relevant, are correct. And the other way around is called recall, like how many relevant are selected. So you don't want to miss anything, right? So you want to look at the two things both for the correlation part. As you can see here, all these numbers, basically the precision recall, they look pretty good to me. You can reach a very high precision, quantitatively speaking. And you will see that, qualitatively next, I think. Yes, right here. Here, I just want to let you guys visualize, how good performance can a recurrent neural network here behave here, right? On the left is a very standard one. So you're driving, and then you're making So you're driving here, right? And then you're trying to make a left turn. And right here, if you see this little green arrow shows up, that means the RNN captures your intention. It predicts your intention, right? Like you're going left. And I'm also doing some of the trajectory prediction, like the blue ones, with some probability is your primary prediction. The yellow ones are just a fallback. So in case someone is changing lane and you decided to fall back to whatever lane you're going before, that's the yellow one. So it's like plan A, plan B kind of thing. And you can just look at it like, it's pretty precise visually, of course. You basically capture every single intention change, transitions of your intentions. Now you might argue that something like this, you can use a simple algorithm, not even an algorithm, like a piece of a code, like heuristic based, right? If the heading angle is larger than some degrees, smaller than some negative degrees, I can do that, right? Maybe the performance is not 99.9%, I can do 99.6%, for example, right? Fine. Now let's look at more challenging cases. So this is what I call like drunk drivers, for example. All these guys are drunk. Everybody's behaving like this. How good can your simple piece of code work in these cases? Like the heading angle is changing constantly, and you want to actually use training, right, to kind of memorize or learn when exactly the intention transition is going to happen. Now, of course, this is not a 99.9%, right? I didn't, quote the numbers here. It's going to be much worse, like 70 or 80%. You can do this, but I just want to show you the power of like training. You throw a tons of data, right? A few 100,000 sequences of data. You train it, and your neural network should be able to capture this, even in this challenging scenes. If you want to look at the full demo, it's here on the YouTube, right? I posted online, just in case people want to do it. Okay, and then the second part is about the behavior part. So now we have all these fundamental units, which we call short-term intention, and then we can work on the behavior part. So I was just, listing all this behavior. We have normal driver behavior, then you have aggressive, then you have suspicious, and then you have high risk, like a drunk driver. And then you have more like conservative driver, like, kind of a very conservative driving behavior. Then I built the behavior from all this, risks, I call risk factor. It's like an investment company, you build a risk portfolio. So you look at all these different factors for risk, like how people do steering wheel, how do they, control the steering wheel? How do they do the car follow in front of the car? Sometimes people trying to follow the car very, closely, right? Small distance. How do you do lane keeping? How do you do lane change? How do you do signal? How do you do speed control? Everything is an individual factor in your portfolio, and you build out a behavior out of that portfolio. It's kind of like a regression problem if you think it that way. Of course, there's some non-linearities inside this, model. And right now, we're also experimenting using data-driven approach, which is like you do training stuff, right? And you want to predict the behavior, but that part is more challenging because a behavior prediction requires few seconds, at least few seconds of observation data, right? You might observe this guy for like 10 seconds, and then you decide this guy is aggressive. And also behavior could change, right, during your driving. So I'm just gonna show you some, of the behavior I'm talking about, like what is aggressive behavior here. right? Because you have a guy driving like this. Every time you see this little weird box says warning on top of it, meaning the algorithm detects aggressive behavior. And this behavior is built out of the risk portfolio I just said, right? How they change lanes, right? They change lanes very fast, very aggressively, right? How they do speed control. And some of them, they don't, like unsafe double lane. So they don't care about the other lane. If you're on this lane, you don't care about the other lane, what the other lane guys is doing, right? They can also be changing lane. They don't care. So that's, aggressive behavior, right? And then, suspicious behavior is sort of a similar, right? You're controlling car, right? This one is very funny, right? Because this guy is turning maybe too small for you, because this guy is turning his left signal on while he's doing this right lane change. You can do that, right? You can classify this as a suspicious behavior. Oh, by the way, all these intentions, like lane changing intentions, is detected by a recurrent neural network, right? So every time when you see that little green arrow comes out, right, it's from the neural network. And every time when I see a suspicious behavior, I want to put a bar on top of it, right, with a question mark, meaning it's suspicious behavior you got to be careful with. So I'm showing all this in the skeleton mode as well, so they can see them clearly. I identify the suspicious behavior as pink, the magenta, and the aggressive behavior as yellow. And then the high risk behaviors, right, that's actually very easy to detect. Just look at how they drive, their intentions, transitions, their maneuvers, right? You can classify a high-risk behavior. So every time when you see a guy with this little box with a high-risk sign on it, that means the algorithm detects this behavior. So these are the features I think it will be very useful in terms of the safety of self-driving cars, right? So you identify the behaviors, the risky ones, the suspicious ones, the aggressive ones, and then you have their intentions, right? And then you can build a platform, right, where you can plug in all this into a safety platform, which I think I will be talking next about this. So here is the first application using this prediction, which is actually my favorite experiment. I call it runway driver experiment. If you look at this setup here, this is the scene. All these white boxes, I call them neighbors. So they're just my neighbors. They're driving. They're having their own business. This blue box is basically my ego vehicle. It's a self-driving car that I care about. This red box here, I call them like quote-unquote assassinator vehicle, which is a drunk driver, basically, in this case. This guy's drunk, all right? This guy can do anything they want. This guy's crazy. And in this case, this guy just won't hit you. So they're going to run across this yellow boundary, right into your lane, head-to-head, right? And I want to see how much importance prediction can help in the collision avoidance in this case, right? So let me just play a little demo that I did before. So I'm driving here, as I said, this guy is coming to your way, and you're trying to avoid it, right? Oh, sorry, I forgot to mention here. There's a different way you can do it, right? You can, the most natural way to do it, since the risk comes from left, human being will swerve to the right to avoid your risk. There's some other counterintuitive one, which is you accelerate. So you run into that drunk guy, and then you left turn because there's a guy here in your way. And an even more ridiculous one is you go left, right? Because you're against traffic rules, so you go left because there's no room on your right. So you go to the left lane to avoid this guy, and then you come back. That's very counterintuitive, right? Human beings would never do that, I believe, right? At least I wouldn't do that. But sometimes you have to because you have nowhere else to go, right? You're forced to do that. So now let's look at this, things. In this demo here, this ego car is just using a simple simulation tree, like a Monte Carlo tree, search, some kind of a thing, to search for my different decisions I should make, right? But what I want to show here is not about the planning part, like how to do collision avoidance. I want to show how much, this is after like you have a 1 to 2 second prediction. So you plug in your prediction part, right? So you're actually predicting this guy is going to the left, and then you do your decision-making processes. So you can see actually sometimes I stop, right, to avoid it. Yeah, and this is a swerve to the left thing we're talking about. So sometimes I have to, since there's a guy here, it's actually in my way, right? And I have to go to left and comes back. And all this, is done with providing our, prediction, that 1 to 2 second prediction. Like I'm predicting this guy is coming, and I should do something about it in advance instead of just wait there to die, right? So that's the key message I want to convey here. And on the right-hand side, of course, I'm doing some measurements, right? Because we're experimentalists. We want to measure stuff. So I'm going to explain this. These blue dots, blue traces, are ego vehicle. These red ones are assassinator, the drunk guy. The orange ones are the neighbors. And you're looking at, this is the x-axis right here, and this is the so-called y-axis, right here. You can see on the left is the one that I actually success, right? Successful trials. So I can actually, sometimes I go right, of course. Most of them I go right, avoid it. Sometimes I have to go left and avoid it, right? So that's the successful one. What is interesting, if you look at the failed ones, I only fail in this case, which means the guy starts to attack me very close to me. Remember, it's head-to-head on a highway. It's very fast. And you're separating by what, like 50 meters or even 70 meters? So I don't have enough time to react. So sometimes, in this case, I will swerve to the right to avoid the collision, but I all failed. And if just by looking at the traces, right, I think I did a rough measurement. I can reach like 75% success rate to avoid this, drunk guy. This is just a typical setup experiment, which I want to sort of to get the message that the prediction is very important here, to avoid these things. If you don't have it, you're going to die no matter what. And the second application is kind of very straightforward, which I talked about this in the very beginning. People are doing self-driving cars, and we are more building a collision forecasting system, or a collision alarming system. So you want to forecast where the collision comes from. And using the prediction part in intention, it is very straightforward to do such things. Very straightforward. Just give you a very simple demo here. If you have, two guys like this, right? And right here, when this green arrow shows up, that means your neural network detects this guy is going right, this guy is going left, right? And then immediately I can draw a yellow box. I call this part a conflict of interest of two guys. This is the high-risk area, which you should avoid, right? So this is what I call like a forecasting. Like this, something is going to happen there with some high risk at some high confidence level. So you better avoid it. This just give you a little taste of like how we can build, applications out of this, sort of like research, right? We can actually implement our research in products. That's what I'm basically telling you. Yeah, as I said, it's pretty quick, right? I don't think it's 45 minutes. Just to summarize very briefly, we built a prototype platform to standardize testing validation for self-driving cars, right? We have data available for training your own AI system, your own neural network. We can provide that. And we're focusing on we're not focusing on sensors, architects, system. That's not our focus. We're focusing on the behavior, intention, risks, collision, scenes, all these different challenging cases. That's our focus. And we're also building our prototype of prediction system for intentions, for behaviors, right? And this prediction will help significantly in challenging things like, runway driver experiments. So that's basically the key message here, why the prediction is so important. I think that's it. Yeah, thank you very much. I guess we have plenty of time to take questions. If you want. Yeah, sure.
So I have a question. I've noticed in different parts of the world, different drivers act differently. In Europe, for instance, in Germany, I noticed they really pay attention to the keep right, pass left. And in the U.S., that isn't necessarily the case. You might have somebody in the left lane going slower than the center lane. Are you gathering data in different parts of the world, and will you have like artificial intelligence models for each area, or are you going to try to make one standard and use it everywhere?
Yeah, that's actually exactly the key point here. I think I didn't mention this. The behavior intention part affect each other mutually. There's a correlation between the two, right? The behavior actually determines how the intention gets executed, right? The different area have different behavior. That's the thing. We have to do behavior in order to do intention. And to answer your question, it is a challenging question. You're going to collect real-world data, either from sensors, that would be better, or you collect from some video clips. You watch how people behave, and that data is going to be fed into the system as an iterative approach to update your behavior model initially that you set up. So it's think of it as like a Bayesian update. You have a prior assumption, you collect data, have likelihood, and you update it. And then finally, you have your post-Terrian distribution for the behavior part. So it's a legitimate question, and it's very challenging to do it. But I think that's the right way to do it, to have the real-world data updating your model.
So but the question is then, do you get real-world data from different markets? Or are you just collecting it like
Yes.
in China
By
or in
different
the
market, you
US?
mean different human being. That's the essence.
Yeah.
Right? Yeah. How different people behave, basically. Yeah.
Okay.
Yeah. Oh, there's one there.
Hi, I got a couple of questions. Once a driver has exhibited abnormal driving behavior, does it stay that way for the rest of the?
Yeah, see, that's the thing I mentioned at the very beginning of the talk. It's sophisticated, right? The behavior of a guy actually changes.
Right.
This is actually the demo that I show here. If you see other people doing, I call it like a group behavior, right? If you see other people are doing this, most of the time you will follow the other guys. Your behavior definitely changes like this. Everybody started running, even though you don't know what's coming on. Because the first guy ran, because the first guy saw the yellow lines, right? The behavior definitely is going to change over the time,
Okay, and for the second question, if, for example, there's an accident beside you, so there's like an offending vehicle and like another vehicle that somehow gets involved with it, do they both get marked as, let's say, aggressive?
Oh yeah, sure. I mean, if you have a runway driver, like if you see this guy here running into your lane like this, right? They're not about to enter your lane yet,
Right.
but you're predicting they're enter your lane. This is gonna belong to like high risk behavior. Right?
Regardless if the vehicle is at fault or
Right.
not.
It's like a drunk driver. It's gotta be drunk, right? Normal guys won't do that, right?
Okay,
Yeah.
thanks.
Cool. All right. Any more? Oh, here. Yeah.
Where do you get your ground truth?
Oh, right now the ground truth is more like generating from the platform itself. So it's more like, it's more like because we're dealing with short-term stuff, right? Like lane keep, lane change, right? So we provide the ground truth to you. So, I have a goal, right? I'm going 280. I want to exit the next one. Then I'm gonna make a lane change to the right lane, and that change to the right lane is my ground truth because I have to fulfill my goal to get out. So I do the lane change, and that lane change is my ground truth, and then I provide that to you for your training labels, basically. Okie dokie. Any more questions, or shall we wrap it up? All right. Thank you so much, guys, for coming to this.